Right, so hello, I'm Parth, and in this video I'll be talking about my project on 8085 microprocessor, and the project is to create a square waveform melody in the A major scale. Now at first sight this sounds like an overly ambitious project, and as we proceed and as you go through the contents of this video and the presentation, you'll understand what I actually mean by making music using 8085. And so what do you need to know to understand the contents of this presentation and the code that I'll be sharing at the end of the video? So first you need to know a little bit about music and specifically about scales. So what makes a scale and what are the frequencies of any scale, say. And second, of course you need to know a little bit about 8085. I'll explain in this video if you have no idea. You need to know a little bit because we'll be coding in 8085. And third, we'll be using GNU Sim 8085, which is a simulator for 8085 microprocessor. It's okay if you don't know how to run that because it's quite frankly not that difficult. And so yeah, these are actually the contents of this presentation. Moving ahead, so you can pause this video and read the disclaimer that I have given because it's actually I haven't actually used the 8085 to demonstrate making sounds at any part of the video. So if you're hoping for that, my apologies, and don't be really quick to judge. So if you thought that I was going to play some 8085 music, then no, sorry, and save your opinions for later. You can write in the comment section. I'll be sure to read it. And so beginning with the music part of the theory. So what are intervals? What are scales? And we don't need to dive deep into the topic. So I'll try to give you a basic understanding of what these are. So in the left side of the screen, you can see the scale names that have been given to the notes. This is the A major scale. So the notes go from A to A. They go as A, B, C sharp, D, E, F sharp, G sharp, and then back A. So in the derivation column, you can see how the frequency of these notes are derived. As you can see, they are basic integer ratios, and from the historical point of view, these notes are made as they are because these integer ratios actually make two notes when played together. This makes it sound better to the human ears, say. And so on the final column, you can see these are the frequencies of these particular notes. So these are actually the traditional frequencies, and they were used way back. And now things are actually different. So on the right side of the screen, you can see the representation of A major scale on a piano, and on the sheet, music. This is actually what we'll call a representation of the scale from A to A. Name it from 1 through 7, and then again 1, because the next A, let's just call it 1 instead of 8, because that is the periodicity of the interval of the scale. I'm sorry. So what did I actually mean when I say that those frequencies were used way back? So to ease, as mathematics progressed and music progressed, say, so for some reason mathematicians came up with this idea of dividing a scale into 12 notes in which the frequencies are played in a geometric progression. So say if the first frequency is F and the second is 2F, then each interval is of the frequency, each interval difference is of the frequency 2 to the 1 over 12th. So the second note is F times 2 to the 1 over 12th. The third note is F times 2 to the 2 over 12th, and so on. On the right side of the screen, you can see this implementation of scale division. This is actually called the 12 tone equal temperament, or the 12 tet kind of division. So this is how they implement it, and these are the frequencies that appear, that we obtain finally. So since I'm gonna use these frequencies to create the A major scale instead of these frequencies. So actually these frequencies, since they are irrational and they are not simple integers, they come in decimals. Every one of them come in decimals. So I'm just gonna ignore that part and treat the frequencies as closest approximation to the integer. So moving ahead, now I'll try to describe what my problem actually is, what this project actually does. So it's really simple. You input some numbers. I'll tell you what those numbers are and what they do, what they stand for. Then the microprocessor is used to process these numbers, and through these numbers it creates a melody out of them. But melody, as the name stands, it creates a square waveform melody. Melody means that in the time domain, the frequencies play as follows. We'll also get to know that these lengths are actually not the same for each one, and uh, one one thing to note is that this length is not actually how it looks in the this is actually the frequency of the note, and the waveform looks different. So don't confuse this with the waveform. And so what my program does is takes these few numbers and uh, maps them to some melody, say. So the numbers will go to the memory, and the final wave will appear in the output port, and it will appear in the output port number 81. So why that port? Because that port is used through the 8255 interface to connect it to an output, any output. Yeah, so how do we go on beginning this project? So I came up with this idea that first we calculate the frequencies. I'll tell you what I mean by calculating the frequencies. Then we design an algorithm to implement the code, and finally we code in the simulator itself. I'll show you that the code actually works, because it will be impossible for me to bring an 8255 in my home and then connect it with an audio output in this time of lockdown. And so there you go. This is actually one of a snippet of the code that I have used in the program. So here you can see this is the mnemonics. These are the mnemonics, and these are the T states that they use. So I'm hoping you're familiar with T states. If not, you can Google them. So these are the T states these programs use, and these are the number of times these programs run in one loop. So this actually gives me the time interval for just take it whatever I'm saying for granted, this code for granted now. This code is actually used to generate a square waveform. That is, it alternates between 1 and 0. So this total I've added up 7 times 1 plus 4 times 1 plus 4 times 2 and so on so on. E here is actually a variable. It's the E register, as you might be familiar with it. So the total delay adds up to this number. And so I've used this total delay, and using some calculations I've derived a formula which gives this is a formula which gives you the value of E, the value that you need to input the register E if you have to obtain a square wave frequency of F. And so here I have calculated the value of E for each note. I have taken the frequencies from this table, the A major scale frequencies from this table, and using that I have obtained the different values of E. So these are the values of E if you need to play the particular note. So keep in mind that we'll use these numbers of E to input, and not this 1, 2, 3, 4 and stuff. So this reference table needs to always be with you if you want to program in 8085 to create square wave melody. For those of you who are interested, this is how the graph looks like of E versus F. And one thing to note is that this. Why did I choose the A major scale? Actually, the A major scale choice was pretty much driven by the fact that the frequency lies in the optimal range. It would be harder to explain like this. If you go through the calculations and arrive at this formula yourself, then you'll understand what I was trying to say. But of course, you can create any number of frequencies with it. Of course, they will be discrete, but the difference between two or consecutive frequencies will not be that much. And so, yeah, feel free to explore, create any of the music you like. There is actually more things than the 12 tet music. There is something called the 19 tet, and so on, so on. You can create a lot of music if you like. So the flow chart of this program, we start, and then the first thing we do is initiate a counter. This counter I have initiated to 2. Why 2? Because the square wave alternates between two states, 1 and 0. So this will loop a square wave. Because it's 2, the first time it decrements, it will come back. It will go to the rotate this loop. As you can see, just ignore everything else and see this counter. It's 2. It comes here, here, here. Then it goes to its decrement. It will become 1 first, so it won't be 0. Then it will go through this loop again, and so the alternate value. For example, if first the value 1 is displayed for the wave, then 0 will be displayed. Then the counter will turn 0, and then the counter will again be initialized to 2, and so we will get the frequency. So what are the other things here? So there's the register A and B being used to store the value AA and 55 in hex. So they correspond to the binary digits 1010 alternating. So the main concept here is this is the traditional way to create a square waveform using 8085. So we use A, and we keep on using this delay and loop. We keep on alternating A between AA and 55 and hex, that is 1010 and 0101, and then we mask A using the hex 01. So we get the least significant bit of A, and we display it as an output. We delay using E, using the register E, and then we go through this loop. Because A needs to be masked using A, mask means AND here. So A also needs to be stored into some other register so that we can go through this loop again. So we use that B for that, and we also use the HL pair. Why do we use the HL pair? Here comes the concept of implementing square waves of different frequencies, that is, in our case, the frequencies of the A major scale. So we point where the HL pointer actually points, we store our input there, and we use E to call that input and put it into the delay box. So as I have shown before, these these values of the E correspond to this note. So I have quite simplified the expression. If you put E equals 240, then the square wave form will be A. If you put E equals 189, the square wave form will be C sharp, and so on. So you can create any of the square wave, and the counter C is actually used to manipulate the length of not one delay loop, but the actual wave that is being generated. So you can create longer music, shorter music, notes of longer and shorter duration using this. One thing you might have noticed is that there's no stop in this flowchart. Why? Because actually you can add a stop. As you can notice, there is one variable missing, which is D. I haven't used the register D, so we can use D to create another loop that will tell us how many times this entire thing needs to run before stopping. However, that comes with one drawback, that is suppose the entire loop runs 5 times, then there's one thing that you will have to input only 5 numbers. That is, you can create a melody of only 5 notes. So if I don't use stop, what actually happens is the program runs as many number of times as you want it to run, and after that, since you have stored the value of 0 in all the other memory locations, this in this formula, if you turn E into 0, then F turns into be a very huge number, around 24 kilohertz, which is beyond the audible human range. So it creates a frequency. So it creates a note of very high frequency which you cannot hear. So of course the power, a lot of power will be used in regularly performing this operation. So, but the thing is that you won't be able to hear anything. So, depending upon your choice, you can either use D or do not use or not use D. I have chosen to go with the second option. And before we move on to the applications, I'll switch to the code and try to explain how I actually coded this flowchart using GNU simulator. Here it is, handy little GNU simulator, and let's start with this part. So first what we do is we move into actually this is a particular command. This isn't something you would be familiar with. This command is used to let the MPU 8085 know that we are interfacing it with 8255 microprocessor. So that's that, and now we initialize H and L with 00 and FF. Why we initialize L with FF? Because here we're increasing the value of L, we're incrementing L, so it will turn to 00 automatically. So the first thing that it will point to is the address 00. Then we initialize B with AA, that is this binary, which will be used, which is the main ingredient for square wave. Now we come to the main program after the initializations. So first we initiate the counter as we saw in the presentation. Then we increment L, now it turns to 0. Then what we do is move the contents of B to accumulator. So the B was AA, now it moves to accumulator. So accumulator will be AA. We rotate the accumulator, so now it turns to 55, that is 55 hex. Now we move A into B so that we can store the 55 for further operations. Now what we do is AND A with 1. So A was 55 and it's ANDed with 1. So 55 is 01010101. When ANDed with 1, it will give the bit 1, and we'll out that bit to port number 81. So here we can, when we execute the program, here we'll see that this number turns to 1. So why this port? Because this port is apparently called the port B of 8255, and we can connect it to many things, for example an oscilloscope. But in our case, because we're coding to make notes of the A major scale, we'll use it to output through the speakers, through any speakers that are compatible with the microprocessor. Now now we move to E the contents of M. So where is M? First, as we have seen, the HL was finally initialized to 00. So what we enter here, the first data bit, is moved to E. Now we use the delay loop using E. So if suppose the first data bit is reads 240 in decimals, then the delay will be such that this one thing to note is that I have not calculated the delay for just this, but the entire thing. So my calculation actually takes into account the entire T states that will be used to create the delay for the wave. So my calculation is pretty much accurate. One thing to note is that there is a bit of asymmetry between the first half of the square wave cycle and the second half of the square wave cycle, but that doesn't really count that much. Of course you won't be able to hear it and explain the difference. So after we have done this delay, we move to decrease the counter as we have seen in the flowchart. That once the counter is decreased, it checks if it's 0. If it not 0, it will move and rotate, and after rotating you can figure out that the same thing will happen, but now the output will be displayed the 0 of the cycle. That is the second half of the square wave cycle. So after this entire thing's run, the C will finally now be 0, and then it will jump back to restart, initializing C again and incrementing L, so that the memory location now points to the next, that is 0001. So it will take this data and do the same thing for as many data as you input. So you can create a melody of any length. Finally, when this is over, of course this is never going to stop, but as I have told, you can use a counter of D and after doing it say 5 number of times, you can redirect it to halt, that is you can jump to halt. So your program will finally terminate. This is the program. Now I'll show you the working. Of course I can show you the working exactly, and even if I use the actual values of E to imitate the notes of the A major scale, actually let me try to do it. Since the first is the A note is 240, I'll input here 240. Now let's start the program. The HL is initialized to 00FF, but here you can see that it will turn to 0000. B is initialized to AA. C is initialized to 2. Now L is incremented and here it turns to 0000. Now the movement of B to the accumulator, rotation turns to 55. 55 goes back to the B register. We AND 55, that is accumulator, with 1 to give the output 1, and the output goes to port number 81. So let's see, this is 81 and it's currently 0. So after we do this, there the 81 turns to 1. So now there's delay, and since I have input the data 240, E is actually F0 right now. 240 is F0. There. So this goes a long number of time. This is why I say that I won't be able to explain my code, but you can see that it runs. Let me shorten this data to say 3, and let me enter the next data to be 4. So these values correspond to some really high frequencies in the audio spectrum, but for the sake of explanation, let's see what's happening. The thing goes as the same. The output port is still 1. Now the decrement is really fast, and the loop is over. Now C is decremented, and you can see it turns to 1. Now if C is 0, no, C is not 0, so it won't go to restart. Now it will go to rotate, because this is an unconditional jump. Back to rotate, and now we do the same thing, but now as you see, since A was AA and it's ANDed with 0, it gives 0. Now outputting to the port number 81, currently it's 1. Now let's see, here it's 0, so 0 will be displayed 3 number of times. Done. C is also 0, so it jumps to restart. Now our pointer, since L is being incremented, there the HL pointer points to the location number this. The same thing will happen, but now E will be 4. So we'll get the wave with frequency corresponding to E value 4. See, it goes 4 times and it does the same thing. So if we increase the value of the counter, say we make it 10, what we actually do is increase the length of our whole square wave, which was earlier just going one round. So yeah, doing this, what we see, actually it should be a multiple of 2, because if you want to obtain both high and low cycles, then the value should be an even number. That's probably occur to you why. Now that's pretty much it about the code, I guess. I hope you understand everything that I explained. The code will be linked in the video, and you can feel free to play with it and create your own changes to this. One thing that I would like to tell you is this code is kind of inefficient. Not inefficient, this is kind of not accurate, because see, the thing is, suppose you take some value of e. This whole loop will create a square wave of that value e, and using this c, that value will repeat. Suppose now you take another value of e, say higher value of e, so the frequency created will be shorter frequencies, which means longer wave pulses. So since the wave pulses are already longer and you keep the value of c the same, thinking that every time you play the notes the same length will come out, so it won't actually happen that way. So there might be a lot of difference between the note durations that are played first and that are played second, because of this error in this program. So this is actually the best that I could come with. If you could find anything else, feel free to write in the comments. Now moving on to the next part of our presentation, I'll finally conclude by talking about some applications applications of this project that I have created. So the first thing that might come to your mind is, of course, making music using 8085. That is good, that is great, and I don't know why people would actually do that if they plan to, other than for nostalgic experiences, say. But yeah, you can do that. And the main thing that came to my mind while thinking about this project is utilizing it in user interfaces. So suppose you have a microwave or a washing machine or anything that runs on a microprocessor, for this case 8085. So when you press the buttons of a microwave or any you go through its interface, you interact with it through the interface. So there is a mechanism in the interface built to tell you that you have touched that button or you have performed this action. So it's a feedback to you. So it's actually a really important part of the product that comes, speaking from the commercial point of view. So this is actually a really important aspect of using microprocessor for creating music. Why I'm saying music instead of frequencies? Because using some specific types of sound, you can using some specific sound, that is sounds from a scale, you can create some because there is an order in a scale, you can create different types of effects that you want on the viewer to have. And music theory, as we all know, has been studied extensively by many of the researchers, by many of the musicians, and there are a lot of ways to create a different sounds. Now I'm going to demonstrate you some of them. I've used a square wave and I've added a bit of post effects on the sound. So this is a sound which would play when you say first boot your system, whatever system it might be. This is the booting effect. I hope you understand why you can feel why it gives the booting effect. Now this is the effect that tells you that a task has been performed. This is the effect that gives you an error message. I hope you're understanding how it's going through. These all notes belong to the scale that I have created in my presentation. This is a simple beep sound that tells you that an action has been performed. And of course you can create some music using this. So with this, I'd like to conclude my presentation, and thank you all for watching. I hope you learned something from this presentation and from the code that I have explained to you. Feel free to use it, feel free to make some changes, and thank you.